So in this video, we are going to see the projective Nullstellensatz. And so what we would like ideally is that when X is projective variety, J is a homogeneous ideal, the best thing would be that VP of IP of X is X, and IP of VP is the radical of the ideal. So, and the idea how to prove this ideal Nullstellensatz would be to use the correspondence from projective variety to cones, and then the cones by the usual Nullstellensatz correspond to some ideals. The problem is that there's a few special cases in the previous proofs. They had these kind of case distinctions, and in particular, one of them is the ideal which is given by the entire ring. Because there we see that, well, the projective vanishing locus of the entire ring, since 1 is in there, is of course the empty set. But then if you take the cone over the empty set, by definition, it always contains 0. And then if you take the ideal of this cone, then the ideal of the origin is that maximal ideal generated by x0 to xn. And you see that is a bit strange because we started with an ideal, then we took projective locus, then we took the cone over this, and then we took an ideal, and then we didn't return to the ideal that we started with. That's a bit worrying if we try to use all these correspondences. So something doesn't commute. Yeah. And then, so we have singled out this ideal. This might be creating problems. And indeed, if we check our ideal Nullstellensatz on this ideal, well, let's take the ideal of the vanishing locus of this thing. Now, the vanishing locus of this ideal is, the claim is this is an empty set. Because, well, you would have to look at all the points where all the coordinates vanish. And if you think about it, that's the one condition that we impose, that all the points in projective space, they cannot be the 0 point. That's excluded. And so the only possible way to be in there would be the 0 point, but it's not actually a point of projective space. So this is the empty set. And then the ideal of the empty set is the entire ring. Everything vanishes on the empty set. And you see, the entire ring is not the radical of this ideal, because it's indeed the maximal ideal, so it's its own radical. So here we see this naive thing cannot quite work. But the good news is that if we just exclude this one troublemaker, this one ideal, then we're good, and then the Nullstellensatz works. And so we define the irrelevant ideal, I0, to be just this maximal ideal inside here, and it is radical, and it is of course also homogeneous because all of these are homogeneous of degree 1. So we call this the irrelevant ideal, and then the projective Nullstellensatz says, well, one direction works very nicely. For any projective variety, we have that it is the vanishing locus of its own ideal. This thing still works. And then if you have a homogeneous ideal inside here, such that its radical is not allowed to be the irrelevant ideal, once you impose this, then it's true that ideal of vanishing locus of J is equal to the radical of J. In particular, so this was the kind of formal properties of VP and IP. And then from this, it follows that you get inclusion reversion bijections between the set of all projective varieties in Pn and the set of homogeneous radical ideals in here, which are not equal to the relevant ideal. And the two correspondences are given by IP and VP, as you would hope. And so the proof, we will skip some parts which work exactly the same way as for affine varieties. Namely, this here, that was the easy part of the usual Nullstellensatz A, and this inclusion here from B, from the right to the left, this work exactly the same as before, and also the fact that these things here are inclusion reversing. This just means if you pose more equations, then you get fewer solutions and vice versa. And so these just work exactly the same. We're not going to repeat this. So the interesting direction is B, somehow this inclusion here, from here to here. So we start with a homogeneous ideal not with radical not equal to I0. Then let's make one case distinction, namely if J contains non-zero constant polynomials. Well, once you have an ideal which contains a non-zero constant, then it is the entire ring. And then we just check by hand, because then the vanishing locus here is the empty set. And this, in fact, gives the entire ring back. And indeed, the radical of the entire ring is also the entire ring. So everything works fine. So let's assume otherwise. So J contains no non-zero constant polynomials. Then we'll define the things that we had before. X is the affine vanishing locus of J inside AN plus 1, and Y is the projective vanishing locus inside Pn. And then we have seen in the proof of this correspondence between cones and projective varieties that indeed X is the cone over Y. This was one of the things that we showed in this proof, using that this condition here is not satisfied for J. So indeed, that is a cone, that is a projective variety. Because this equation here holds, then we saw that taking the cone and taking the projectivization are inverse. So the fact that X is the image of Y under C means that Y is the image of X under the projectivization. So that's good to know. Now we're in a business where these correspond to each other nicely. And then we can apply the usual Nullstellensatz for the cone X, and then we see the ideal of the vanishing locus of J is the radical of J. By assumption, this is not equal to I0, and I0 is the vanishing ideal of the zero locus. That's exactly the maximal ideal corresponding to the single point. So we have seen the ideal of X is not equal to the ideal of 0. And so because taking the vanishing ideal is a bijection between affine varieties and radical ideals, it means that X is not equal to the empty set, not equal to the 0 set containing only the origin. And well, so this is not just 0, it contains at least some other elements. And then these, by the projectization, will give us elements of Y. So from this here, we conclude Y is not the empty projective variety. And you see here, this part you can see basically as proving kind of a weak Nullstellensatz, which says that if J is not the full thing, and it is not, by assumption, the irrelevant ideal, then there is at least one projective solution. So we have kind of proven already the weak part of the Nullstellensatz. And now we want to finish the whole thing. And so now we go really for proving this inclusion here. So we compute IP of dp of J, which we called Y. And then what is it? By definition of IP, it's the ideal generated by all homogeneous polynomials vanishing on all of Y. And spelling this out, what does it mean that this homogeneous polynomial vanishes at this point of projective space? It just means it vanishes on all points in the pre-image in this cone over Y. So it vanishes at all points of X minus the origin. So when you look at this equality here, this is almost the same thing as saying this is the ideal generated by homogeneous polynomials vanishing on all of X. If we had that, then this would basically be the ideal of X. And we want to claim this is indeed true. So what we have to show is that if a homogeneous polynomial f satisfies, it vanishes at all points of X minus 0, then it also vanishes at 0 itself. This is the claim here. And we can distinguish two parts. If f is a homogeneous polynomial of positive degree, then it's automatically vanishing at 0. So that's fine. If it is in the R0, so if its degree is 0, then since X minus 0 is not empty, it must actually be the zero polynomial. Otherwise, it wouldn't vanish on x minus 0. If it was a constant non-zero polynomial, it wouldn't vanish here. So the only way left is that f is the zero polynomial, which obviously also vanishes at the origin. So we could distinguish two cases and then finish the claim. So IP of y is the same thing as the ideal generated by homogeneous polynomials vanishing on x. So it's the ideal generated by the homogeneous elements in IA of x. But this was a homogeneous ideal. This was what we had seen before. The ideal of a cone is generated by its homogeneous elements. It is a homogeneous ideal. And so this whole argument proves that IP of y is equal to IA of x. But then we had seen here IA of x is the radical of j. In fact, here we did prove the full equality, not just the inclusion after all. Okay. And so this finishes the two first parts. And now it's just about the bijection. Why does the bijection work? So just recall, copied from above, this was the claim. And then, well, first of all, we want to check that this is a well-defined map between these things. Clearly, if we start with a homogeneous radical ideal, take its vanishing locus, you get a projective variety. The opposite way, if x is a projective variety, so it is given by some VP of j, or j homogeneous, then this here is equal to the radical of j, and we have that this is not, the claim is that this is not equal to the irrelevant ideal. And to show this claim, assume otherwise, assume that IP of x was the radical, was this ideal I0. Then, well, by the first part of the Nullstellensatz, we have x is the vanishing locus of its own ideal. We plug this in, so we get the vanishing locus of the relevant ideal. But we saw this is the empty set. And now we get a contradiction because the ideal of the empty set is equal to the full ring, whereas we assumed that the ideal of x is equal to I0. So this gives a contradiction. And so we know this map IP of x can never hit this irrelevant ideal. That's one of the reasons why it's called irrelevant. And so, okay, we have seen that this is a well-defined map. These are two well-defined maps. And then A and B show that these are indeed inverse to each other. Once you exclude this thing, the two compositions give the identity. So this was the proof of the Nullstellensatz, and we saw, and basically we reduced to the affine case, but there were all these weird little edge cases to check. And to visualize why all these edge cases exist, I wanted to draw up one big diagram. And I know it's a big, intimidating diagram, but let's look at it slowly. So here we have three corners. Here we have the projective varieties in Pn. Here we have the homogeneous radical ideals in the polynomial ring. And here we have the cones. And more or less all these should correspond bijectively to each other. And the one place where this worked very nicely is we have seen in the previous video projective varieties and cones correspond to each other via these two maps here. So for example, the whole projective space corresponds to the whole affine space. And then the linear subspaces here cut out by a single equation correspond to corresponding linear subspaces of codimension 1 inside here. And importantly, the empty set corresponds to the zero cone. So this thing here works very nicely. What we have seen in today's video is that that these two maps here define more or less equalities between varieties and homogeneous radical ideals. For example, the whole projective space corresponds to the zero ideal. this hyperplane corresponds to the ideal generated by a single polynomial of degree 1. But then here we see there's some trouble because both the irrelevant ideal and the full ring have the same vanishing locus, which is the empty set. Whereas the empty set, if you take the ideal, then you get the full ring. So here, kind of the irrelevant ideal is the one left out. It's kind of superfluous. And so if you exclude this, then the Nullstellensatz says you have a perfect bijection here. The reason why it's a bit awkward is that, so here for this bijection, the I0 was the bad guy. But you could also try to go between cones and homogeneous radical ideals by the usual affine vanishing loci and ideals. And there it turns out that the other guy is the bad guy because, well, the affine vanishing locus of the full ring is the empty set because 1 is in there. And by our definition, the empty set is not actually a cone because we always require 0 to be in here. So here, this doesn't really map to this part. And the correct thing corresponding to the minimal element 0 here is the irrelevant ideal. And so the fact that these diagrams don't quite commute, this was the reason why we had to always make a little bit of case distinction here. The good thing is in this diagram, if you remove the empty set here, you remove these two over here, and you remove the 0 cone, then afterwards the diagram is perfect. All the maps are bijections, everything commutes. That's what we showed over the course of the many proofs. But somehow that's just one thing that one has to get used to with the projective varieties. There's always these few complications because you restrict the homogeneous polynomials, and you have to be a bit careful about this irrelevant ideal versus the full ring. Okay, so I hope this diagram made things clearer rather than less clear. But anyway, we have finished the discussion of the projective Nullstellensatz now. Sorry, I take everything back. We haven't finished the discussion of the Nullstellensatz yet because I wanted to add some more properties of the projective vanishing locus and ideal, similar to the things that we have seen in the affine case. And all the proofs will actually just be the same as before. So we're not going to repeat them here. And so the properties here, let's start with sets of homogeneous polynomials. Then you have that the union of two vanishing loci is the vanishing locus of the product of the corresponding sets. And arbitrary intersections of these vanishing loci are just the vanishing loci of the union of all these polynomials. There's also a variant when you start with homogeneous ideals, because the union of their vanishing loci is not just the vanishing locus of their product, as follows from here basically, but it also is the vanishing locus of their intersection. And the intersection of vanishing loci corresponds to the vanishing locus of the direct sum, or just the usual sum of ideals. So that was one direction. And then in the other direction, if you start with projective varieties, the ideal of their union is the intersection of their corresponding ideals. And then the one slightly tricky one is that the ideal of the intersection, you distinguish two cases. If the sets are disjoint, then the ideal, well, the intersection is the empty set, and then the ideal gives the full ring. And you can detect these being disjoint, you can convince yourself this is equivalent to the radical of their sum being the irrelevant ideal. So here this thing pops up again. And if that is not satisfied, and they're not disjoint, then the ideal of this intersection is just what you would hope is the radical of their sum. This now really finishes the basic properties of IP and VP.